So the car industry has been undergoing a radical transformation, and with most car makers agreeing that the next 10 years will bring more change than the two previous decades. So the next target date cited by automakers as a tipping point is 2025. When everything from materials and fuel costs and the companies that build cars are set to look dramatically different. So automakers are preparing to phase out cars powered solely by internal combustion engines as government look to tackle fuel emissions. And the growth in electric vehicles and hydroelectric vehicles is climbing, and by 2025, EVs and HEVs will account for an estimated 30% of all vehicle sales. Now by 2030, the market share for internal combustion engines is expected to fall to around 40%. So vehicle manufacturers are constantly faced with the challenge of balancing fuel efficiency and safety against the demands for greater performance and lower development costs. Now, safety is the most important factor for electric car batteries. Even a single battery fire could turn public opinion against electric mobility and set back industry development and progress for months or even years. So the main concern in this area is avoiding thermal runaway, potentially resulting in a fire. This can be caused by overcharged battery, too high discharge rates, or a short circuit. But while battery safety is indisputably a valid concern, it's useful to put this concern into perspective by recalling safety challenges originally associated with the internal combustion engine, for example, which was largely overcome through improvements in design and engineering. So another factor to consider is lifespan. There are two ways of measuring battery lifespan: cycle stability, or number of charges and discharges, and overall age of the battery. Now, this remains a hurdle in electric vehicles, and it's unclear how various batteries will age across temperature conditions. So it's crucial that accurate battery modeling be implemented to try and understand degradation and what to expect here. Another factor, similarly, is the expectation that an owner of an electric vehicle should be able to drive it both in hot summer temperatures and at sub-zero winter temperatures, especially where we are in Canada, which poses substantial engineering challenges. Now, batteries can be optimized for either high or low temperatures, but it can be hard to create that balance for both extremes without experiencing significant performance degradation. We also have to consider specific power and energy. Now, specific energy is the capacity for storing energy per kilogram of weight, and currently limits the driving range of electric vehicles between charges. And specific power is the amount of power that batteries can deliver per kilogram of mass, and is addressed relatively well by current technologies. You also have to look at charging times. So long charging times present another challenge and a commercial barrier that also must be addressed. So in order to support these developments and balance trade-offs, high-fidelity battery models are required to provide accurate estimates of realistic battery behavior. So battery models allow for the evaluation of battery performance in large systems, and these models also provide access to system-level equations, providing further insight into battery operations. One of the most important components of a hybrid electric or fully electric vehicle is the battery itself. So having a good virtual model of the battery is essential so that both battery behavior and the physical interaction of the battery with all the other components are properly reflected in the model. Since the battery plays such a vital role in the vehicle, capturing these interactions is essential to designing an efficient, effective electric vehicle. So system-level modeling is an extremely effective approach for engineering design projects that can help reduce development time, uncover problems early in the development cycle, and improve overall designs. So by using a system-level modeling tool like MapleSim battery-powered systems can be modeled far quicker than traditional techniques while still preserving accuracy. So with a battery model, you can save time and avoid problems by taking battery behavior into account early in the design process. You're able to understand loading effect on the battery as it undergoes many different duty cycles and how the battery will behave as part of the greater system. You gain a better understanding of the heat flow in the battery, how rising temperature and age affects efficiency, and what critical factors could cause thermal runaway. You can also easily adjust your designs to optimize performance and reduce many of those risks that we talked about in previous slides. So the multi-physics and parametric nature of MapleSim make it especially well suited to implementing a realistic battery model. And the MapleSim battery library allows you to incorporate physics-based predictive models of battery cells into your multi-domain system-level models. So using MapleSim, batteries can be modeled and simulated with high accuracy and fast simulation times. The two modeling approaches used in MapleSim are equivalent circuit-based models and electrochemical-based models. So circuit-based models use electrical circuits that reflect the charge capacity and internal resistance through the use of standard electrical components to represent these properties. These equivalent circuit models are conceptually simple but are capable of capturing many of the nonlinear behaviors within the cell. The component models can easily be incorporated into any larger system model and are generally not computationally expensive. However, their scope of operation is somewhat limited, and it's not easy to map the components of the model to the physical aspects of the real cell. On the other hand, electrochemical models explicitly represent the chemical processes that take place in the battery. These types of models describe the battery physics in great detail, making them the most accurate of all battery models. This physical behavior can be represented by a system of well-documented PDEs. However, solving these equations can only be achieved through the use of computationally intensive techniques. This often makes them unsuitable for system-level modeling, since they can take hours to compute the behavior of the battery over just a few seconds. By simplifying the model to a set of ordinary differential equations, MapleSim provides real-time performance while sacrificing very little accuracy of the full physics models. So as manufacturers face the challenges of delivering products that are economically attractive while fulfilling their environmental and legal demands placed on them, complex mathematical models of the products are becoming increasingly important and increasingly complex. The flexibility of component-based modeling within allows development of highly accurate and customizable battery models. These new battery models can then be incorporated into larger system models, allowing the development of the complete system by integrating the various subsystems into one environment. So these subsystems can come from various engineering domains, such as mechanical, electrical, chemical, thermal, and so forth. It uses a schematic approach to defining the model. You simply connect components together, and the environment of MapleSim takes care of the math for you. So once the model has been created, the system equations and parameters are available for analysis and optimization, allowing you to not only ensure that the system will work, but enabling higher performance while reducing development costs. So at this point, I'm going to show you a similar model to the one I was just working with in the previous slide. I'm going to open up MapleSim. So I have a little bit of a simpler model, so not full system with all the components. But here we have an electric vehicle. It's powered by a battery here. We have a couple of probes. So we've got battery temperature, its state of charge, We're also looking at vehicle speed over time. So we've got the speed control built in there. I can run the simulation. So we can see it's generating the equations. It just takes a few seconds in here. And what we'll get is several plots over time. So what we're interested in is the vehicle performance. So what's happening here, we've got quite a few of them. So I can run this again, but we've got the vehicle speed over time, we've got battery voltage, we've got our battery current. We also have battery temperature, which we talked about quite a number of times. It's quite important to consider in battery modeling. We also have our state of charge over time. So our simulations run through at this point and is finished, so I can start. Smaller, so we can see all of them on one. That's running for 800 seconds. If we run that again, we can watch them all at the same time. But again, as we see it running and generating that data, at any point along here we're losing charge or temperature. In this case is decreasing only slightly, and it is in Kelvin. That can be changed depending on what probe you're using, and that's also our vehicle speed dropping here. If we go back into our slides, so what you can look at is battery load analysis and optimization. So if those weren't the results you were looking for in that case, that model can be played around with, tweaked with. So again, that's just the simulation. So if that's not the results, that's not the actual data. So at that point you can change out the battery. You can change what type of battery you were using to get more of what you wanted it to look like. Change the materials you're using. You can do hardware in the loop testing, the thermal modeling and cooling system optimization, your study of mechanical loading effects, state of health effects, so again that's your state of charge, looking at your degradation of your battery,